There is a comfort to be found in the immutability of the night sky. For thousands of years, civilizations have risen and fallen, empires have crumbled into dust, and the geography of our own planet has shifted beneath our feet. But the stars have remained. They are the silent witnesses to our history, fixed points of light that navigators have trusted to guide their ships across dark oceans, and farmers have watched to mark the turning of the seasons. We grow up learning their names and their shapes, finding reassurance in the fact that when we look up on a cold winter night, the constellations will be exactly where we left them the year before. Among these celestial fixtures, few are as recognizable or as commanding as the hunter Orion. Dominating the northern hemisphere's winter sky, the hunter stands tall, his three-star belt a perfect line of cosmic geometry. And at his right shoulder, or the left as we see it from Earth, burns a beacon of deep, ruddy orange. This is Betelgeuse. It is one of the 10 brightest stars in our entire sky, a red supergiant that acts as a lighthouse in the dark, contrasting beautifully with the icy blue-white of Rigel at the hunter's foot. For generations of stargazers, Betelgeuse has been a constant companion, its fiery glow a familiar warmth in the freezing vacuum of space. But in the dying months of the year 2019, that sense of permanence was shattered. It began slowly, almost imperceptibly. In October, seasoned astronomers and amateur sky watchers alike began to notice that the great red star seemed a little less lustrous than usual. At first, this was dismissed as nothing more than the star's natural rhythm. We have known for a long time that Betelgeuse is a semi-regular variable star. It breathes, it pulsates, its brightness rises and falls over cycles of roughly 400 days and longer stretches of nearly 6 years. A dip in brightness was not, in itself, a cause for alarm. It was simply the star doing what it had done for eons. However, as the weeks wore on and the calendar turned toward December, the dimming did not stop. It accelerated. By the time the holiday season arrived, the change was no longer the domain of sensitive photometers or careful data analysis. It was visible to the naked eye. If you stepped out into your garden on a clear, crisp night in January of 2020, you would have seen something deeply unsettling. The shoulder of Orion, usually a powerhouse of light that rivals the brightest jewels of the heavens, had faded to a ghostly, pale imitation of itself. It was dimmer than Aldebaran, the red eye of the bull in the neighboring constellation of Taurus. It was fading past Bellatrix, the hunter's other, usually much fainter shoulder. For those of us who look at the stars with the affection one holds for an old friend, the sight was visceral. It felt as though a light was being extinguished. The architecture of the winter sky of our Pasai pattern that had held firm since before the pyramids were built was breaking. This event, which would come to be known as the Great Dimming, triggered a wave of excitement and trepidation that rippled far beyond the scientific community. The question on everyone's lips was as simple as it was terrifying. Is this the end? We know that Betelgeuse is a star living on borrowed time. It is a massive star, roughly 15 to 20 times the mass of our Sun, and massive stars live fast and die young. While our Sun will burn steadily for billions of years, a star like Betelgeuse burns through its nuclear fuel with voracious intensity, reaching the end of its life in just a few million years. The final act of such a star is a supernova, a cataclysmic explosion so bright that for a few weeks it can outshine an entire galaxy. When Betelgeuse finally detonates, it will be a spectacle unmatched in human history, It will shine with the intensity of a half moon, casting shadows on the ground at night and remaining clearly visible even in the broad light of day. It will act as a second sun, a piercing point of blue light that will transform our sky for months. So, when the star began to plummet in brightness in late 2019, the immediate, hopeful, and fearful conclusion for many was that we were seeing the prelude to this detonation. Was the dimming the deep breath before the scream? Was the core collapsing, causing the outer layers to implode before the rebound shockwave tore the star apart? Headlines across the world announced that the explosion might be imminent. Social media was ablaze with speculation. Every telescope capable of pointing at Orion was swung toward the red giant, capturing data with frantic urgency. We were watching a celebrity on their deathbed, waiting for the final moment. But to understand why this behavior was so baffling and why the supernova theory was both plausible and yet professionally doubted, we must first understand the sheer, incomprehensible scale of the object we are discussing. Betelgeuse is not merely a large star. It is a monstrosity of physics that defies our intuitive grasp of volume. If you were to take Betelgeuse and place it at the center of our own solar system, replacing the Sun, it would not just swallow Mercury, Venus, and Earth. It would consume Mars. Its surface would extend out past the asteroid belt, likely engulfing Jupiter. Imagine that for a moment. A single star so vast that if you flew a commercial airliner at 900 kilometers per hour along its surface, it would take you centuries to complete one circumnavigation. Yet, despite this colossal size, Betelgeuse is incredibly light for its volume. It is what we might call a red-hot vacuum. Its outer layers are so diffuse, so tenuous, that they are thinner than the air at the altitude where the International Space Station orbits Earth. If you were to somehow float at the surface of Betelgeuse, a boundary that is itself incredibly hard to define, you would not be standing on a solid crust or even a thick ocean of plasma like you might imagine on the Sun. You would be drifting in a glowing, superheated fog, a red haze that stretches for hundreds of millions of kilometers. This low density means that the gravity at the surface of Betelgeuse is pitifully weak. On Earth, gravity holds our atmosphere tight against the rock. On the Sun, the immense gravity keeps the plasma in check. But on Betelgeuse, the outer layers are barely holding on. They are loosely bound, drifting and billowing like smoke in a drafty room. This makes the star inherently unstable. It is a bubbling, boiling cauldron of convection currents. Huge cells of hot gas, some as large as our entire solar system, rise from the deep interior to the surface, where they cool and sink back down, causing the star to brighten and dim over time. This instability was well documented. In 1836, the great astronomer Sir John Herschel was the first to rigorously describe the variability of Betelgeuse, noting how it sometimes outshone Rigel and other times faded into the background. Aboriginal Australian oral traditions, stretching back thousands of years, also speak of the star's changing fire, describing it as Nyaruna, a figure whose fire magic waxes and wanes. We knew the star was fickle, but the great dimming was different. By February 2020, the brightness of Betelgeuse had dropped to roughly 35% of its usual luminosity. It had fallen from magnitude 0.5 to nearly magnitude 1.7. In the logarithmic scale astronomers use to measure brightness, this was a precipitous collapse. It was the faintest the star had been since records began a century and a half ago. This was not just a deep cycle, it was an anomaly. Edward Guinan, an astronomer at Villanova University who had been monitoring the star for decades, watched the data points drop night after night with a mixture of professional fascination and personal disbelief. The curve on the graph was not bottoming out, it just kept going down. The fainting of the star was so severe that it began to challenge our models of how red supergiants behave. If this was a pulsation, it was a pulsation so extreme it risked tearing the star apart. If it was a cooling of the surface, the temperature drop required to dim the star, this much would have to be catastrophic. The supernova theory, while exciting, began to lose traction among the experts as the weeks went on, even as the public hype reached its peak. The physics of a core collapse are brutal and fast. While a star might show some instability before it explodes, the process is usually governed by the exhaustion of fuel in the core. When the iron core collapses, the result is instantaneous on cosmic timescales. There is no known mechanism that would cause a star to slowly dim over 4 months before exploding. If anything, we might expect a sudden brightening or a neutrino burst. Betelgeuse was just getting quieter and quieter, like a candle flame dwindling in a sealed jar. Then, just as the tension reached its breaking point, the star pivoted. In late February 2020, the dimming stopped. The curve flattened. Slowly, agonizingly, the light began to return. Throughout the spring of that year, Betelgeuse brightened again, reclaiming its status as a top-tier star. Though it looked somewhat weary from the ordeal, the explosion did not happen. We were not treated to the fireworks display of the millennium. The Earth was not bathed in the light of a second sun. But what we were left with was a mystery that was, in many ways, far more compelling than a simple explosion. Something happened to Betelgeuse in late 2019. Something violent, massive, and unprecedented in the era of modern astronomy. It was an event that blocked out the light of a star billions of times the volume of our sun. It fooled our eyes and confused our sensors. It forced us to look at this red giant not just as a ticking time bomb, but as a dynamic, living world with weather, geology, and a chaotic environment that we are only just beginning to understand. To solve this mystery, we could not rely on simple telescopic observations from the ground. The atmosphere of Earth blurs our view, turning stars into twinkling points of light that hide their secrets. We needed the power of our greatest observatories. We needed the Hubble Space Telescope, peering from orbit with its crystal-clear vision. We needed the Very Large Telescope in the Atacama Desert of Chile, using its adaptive optics to cancel out the shimmer of the air and resolve the disk of the star itself. And when we finally processed those images, when we looked at the face of the star during its darkest hour, we saw something that defied expectation. The star hadn't just dimmed uniformly, it had changed shape. The bottom half of the star, the southern hemisphere, had essentially vanished. It looked as though a great bite had been taken out of the disk, a dark shadow creeping across the face of the god. This was the first clue in a detective story that would take another year to unravel. It was a story that would involve a violent ejection of matter, a sudden drop in temperature, and the formation of a cosmic veil. It was a story that would teach us that while Betelgeuse may be dying, it is certainly not going quietly. It is fighting, thrashing, and belching out the raw materials of creation into the galaxy, even as it teeters on the brink of its final collapse. As the star returned to its normal brightness, leaving astronomers to pore over terabytes of data, a realization settled in. We had witnessed a rare convulsion in the life of a supergiant. We had seen a mass loss event on a scale that is hard for the human mind to comprehend. But this was only the first layer of the puzzle, because as we looked closer at the data, as we analyzed the heartbeat of the star and the strange rhythms that pulse beneath its surface, we found that the great dimming was just one symptom of a much deeper strangeness. There are ghosts haunting Betelgeuse. There are cycles that shouldn't exist. There are rotations that defy the laws of angular momentum. The Great Dimming was merely the opening act of a scientific drama that has fundamentally rewritten our understanding of how these stellar behemoths live and die. We thought we knew Betelgeuse. We thought it was just a big red dying star. But the darkness of 2020 showed us that we were wrong. The star is hiding secrets in its glare, and to find them, we have to look past the light, into the dust, and the gas, and the shadows. We have to understand what exactly happened during those cold winter months, and how a star can effectively disappear in plain sight. The answer lies not in the core, but in the chaotic, turbulent atmosphere above it, a place where the laws of thermodynamics play out on a canvas nearly 1 billion kilometers wide. When the European Southern Observatory released the images of Betelgeuse taken in December 2019, the astronomical community collectively drew a breath. For decades, stars were little more than pinpoints of light to us, unresolved dots that could be analyzed for their chemistry and temperature, but never truly seen as places. Even through our most powerful optics, the vast majority of stars remain singular, pixelated specks. But Betelgeuse is different. Because of its immense size and its relative proximity to Earth, it is one of the very few stars whose surface can be resolved as a disk, provided one has a telescope powerful enough. The images from the Very Large Telescope in the high, dry desert of Chile were grainy, glowing orbs of orange and red, but they showed something undeniable. The star was not fading uniformly. It was not simply turning down a dimmer switch on its global energy output. The southern hemisphere of the star had gone dark. It was as if a heavy curtain had been drawn across the bottom half of the supergiant's face. This asymmetry was the smoking gun that shifted the conversation from a fear of imminent death to a mystery of stellar mechanics. To understand what we were seeing, we had to choose between two competing theories. The first was that Betelgeuse had developed a colossal star spot. We are familiar with sunspots on our own local star, cooler magnetic storms that appear as dark blemishes on the solar surface. These spots are huge by Earth standards, often large enough to swallow entire continents, but compared to the sun itself, they are tiny. For Betelgeuse to dim so significantly due to a spot, the spot would have to be monstrous. It would need to cover at least half of the visible surface of the star. A magnetic storm of that magnitude would suggest a stellar physiology completely unlike anything we observe in the solar system. The second theory, and the one that would eventually win out, was less about the star itself and more about what was happening in the space immediately in front of it. This was the dust hypothesis. The idea was simple but profound. Perhaps the star was shining just as brightly as ever, but something had moved between us and it. A cloud. A dense, opaque fog of cosmic soot that was blocking the light before it could reach our telescopes. But where would such a cloud come from? In the emptiness of interstellar space, massive clouds of dust do not simply wander in front of stars by coincidence. If there was a veil hiding Betelgeuse, the star must have made it itself. The forensic reconstruction of events began by looking backward in time. While the dimming peaked in early 2020, the trigger for the event had occurred months earlier. Astronomers looked back at data collected by the Hubble Space Telescope in the autumn of 2019, long before the visible light began to fade. Hubble sees the universe not just in the light our eyes can perceive, but in ultraviolet, the high-energy light that reveals the violent, hot processes happening in the upper atmospheres of stars. In those ultraviolet records, researchers found the prelude to the drama. In September and October, Hubble had detected a massive flare-up of hot, dense material moving through the star's atmosphere. It was a dense parcel of plasma, hotter and brighter than the surrounding surface, surging outward at speeds of over 300,000 kilometers per hour. This was a surface mass ejection, a titanic burp of stellar material. To visualize this, we must strip away our earthly sense of scale. The convective cells on Betelgeuse, the bubbling pots of plasma that bring heat from the core to the surface, are not like the bubbles in a boiling kettle. A single one of these granules can be the size of the orbit of Jupiter. In the latter half of 2019, one of these colossal convective cells bubbled up to the surface. It was energized by the shock waves of the star's natural pulsation cycle, which happened to be expanding at that exact moment. The combination of the upwelling gas and the outward push of the pulsation proved too much for the star's weak gravity to contain. The material broke free. A cloud of plasma, weighing millions of times the mass of our moon, was launched into the void. At this stage, the material was still incredibly hot, glowing brightly in the ultraviolet spectrum. It was transparent, searingly bright, and invisible to the naked eye as a separate object. To an observer, it would have just added a fraction more luminosity to the already blinding star. But as this ejecta traveled away from the surface, coasting outward into the freezing vacuum of space, it began to change. Space is cold. As the gas expanded and moved millions of kilometers away from the heating warmth of the star, its temperature plummeted. It dropped from the searing thousands of degrees of the surface down to a relatively chilly 1,000 degrees or less. And this is where the alchemy of the cosmos takes place. When gas cools sufficiently, the atoms within it lose their frantic energy. They stop bouncing off one another and begin to stick. Heavier elements like silicon, magnesium, and aluminium, forged in the nuclear furnace of the star's previous life stages, began to bond with oxygen. They formed molecules of silicon monoxide and aluminium oxide. In simple terms, the gas was condensing into solid rock. It was turning into dust. On Earth, we think of dust as a nuisance, the gray fluff that gathers under the bed, or the dirt on a windowsill. But in astronomy, dust is the stuff of creation. It is microscopic grains of smoke, sand, and glass. And crucially, while gas is often transparent to visible light, dust is opaque. A cloud of gas allows light to pass through it. A cloud of dust acts like a brick wall. As the ejected material from Betelgeuse condensed into these solid grains, a dark cloud rapidly formed in the star's vicinity. Because of the trajectory of the ejection, this cloud was not blown off to the side where we would see it as a bright nebula. It was blown directly toward Earth. It positioned itself perfectly between our line of sight and the southern hemisphere of the star. Imagine standing on a foggy night, watching a distant street light. If a puff of thick black smoke were to drift in front of the lamp, the light would dim, turning orange and deep red before vanishing. This is exactly what happened to Betelgeuse. The star didn't cool down. It was eclipsed by its own exhaust. The great dimming was, in essence, a great dusty sneeze. This confirmation came from a synthesis of data. While the visual light dropped, the infrared light, which is emitted by warm dust, remained surprisingly bright. The dust grains were absorbing the starlight, heating up and glowing in the infrared, even as they blocked the visual light we see with our eyes. It was a perfect conservation of energy. The missing light wasn't gone. It was just being shifted into a different part of the spectrum. This event has given us a profound window into the relationship between red supergiants and the galaxy they inhabit. We have known for a long time that stars like Betelgeuse are the great polluters of the cosmos. They are engines of enrichment. The universe began with only the simplest elements: hydrogen, helium, and a trace of lithium. Everything else, the carbon in our cells, the oxygen we breathe, the silicon in the computer chips running our world, and the iron in our blood, was forged inside the cores of stars. But having those elements inside a star is of no use to a planet. If the elements stay locked in the core, they die with the star. For life to exist, those elements must be liberated. They must be cast out into the galaxy to mix with interstellar clouds, eventually collapsing to form new star systems and rocky worlds. Supernovae are the most famous mechanism for this dispersal, explosive events that scatter heavy elements across thousands of light years. But the great dimming of Betelgeuse proved that red supergiants do not wait for death to begin this process. They are shedding their skin while they are still alive. Through events like the one we witnessed in 2019, Betelgeuse is slowly losing its mass. It is stripping itself of its outer layers, seeding the surrounding space with heavy elements. The dust cloud that formed in front of the star has now drifted away, expanding and thinning out into the interstellar medium. Millions of years from now, those same grains of silicon and aluminium that confused astronomers in 2020 may find themselves clumped together in a protoplanetary disk, forming the crust of a new planet orbiting a new star. The realization that the dimming was caused by dust also solved the mystery of the star's shape. The bite taken out of the southern hemisphere was simply the silhouette of the cloud. As the cloud expanded and dissipated, the light of the star returned to normal, not because the star reignited, but because the fog cleared. By April 2020, Betelgeuse was back to its brilliant self, the obstruction gone. However, the sheer magnitude of this ejection raised new questions. We have seen stars lose mass before, but usually in a steady, gentle stream known as a stellar wind. This was different. This was violent, localized, and episodic. It suggests that the outer atmosphere of a red supergiant is far more volatile than our previous models assumed. It is a place of violent weather, where magnetic fields and shock waves dance in a chaotic ballet. The dust cloud hypothesis was further solidified by the color of the star during the dimming. Observers noted that while the star got fainter, it didn't get significantly redder in the way a cooling star would. If the surface temperature had dropped globally, the color spectrum would have shifted dramatically toward the infrared. Instead, the color remained relatively stable, consistent with a blockage rather than a transformation of the source. The dust grains were large enough to block light across the visible spectrum, acting as a neutral density filter, sunglasses for a star. As the excitement of the supernova scare faded, a sense of awe replaced it. We had watched a stellar process play out in real time, We had seen the creation of stardust on a human timescale. Usually, astronomy is the study of static snapshots. We see a nebula here, a star cluster there, and we infer the motion over millions of years. But with Betelgeuse, we watched the movie. We saw the ejection, the cooling, the condensation, and the dispersal. The dust cloud of 2020 was a reminder that Betelgeuse is not a static ball of gas. It is a dynamic, evolving object. And while the dust explained the dimming, it did not explain everything. Why did the ejection happen exactly when it did? What triggered that massive upwelling of gas? Was it just random chance, a roll of the thermodynamic dice? Or was there a deeper rhythm at play? To answer that, we must dive below the surface. We must look past the dusty veil and into the deep interior of the star. For while the dust explained the symptom, the cause lies in the heartbeat of the monster. Betelgeuse pulses. It expands and contracts like a breathing lung. And it was the synchronization of this heartbeat with the surface turbulence that launched the cloud. But as astronomers looked closer at these pulsations, they found something that didn't quite fit. The star beats with a primary rhythm, a fundamental cycle of about 400 days. But overlaid on this is a secondary, much longer cycle, a slow, deep rhythm that repeats every 2,170 days. This long secondary period is a ghost in the data. It is too long to be a simple pulsation of the star's envelope. The physics of sound waves bouncing around inside the star cannot easily explain a cycle of 6 years. This mystery draws us inward. We have solved the riddle of the shadow, but the riddle of the timing remains. Why does Betelgeuse act like a clock with two different pendulums, one ticking every year, the other tolling every 6? The answer to the dust ejection may be simple physics, but the trigger for it connects to the very structure of the star itself. As the dust cleared in late 2020, the view of the star was restored, but our understanding had been permanently altered. We no longer look at Orion's shoulder as a mere point of light. We see it as a bubbling, smoking factory, a place where the raw heat of the core battles against the cold of space, creating the soot that will one day build worlds. The great dimming was not an ending, but a demonstration of creation. Yet, the questions lingered. The dust was the how, but we were still searching for the why. And as we analyzed the long-term cycles of brightness, the 6-year rhythm began to stand out as an anomaly that refused to go away. It is a rhythm that hints at something unseen, something external to the star, or perhaps something deeply buried within. The dust has settled, but the investigation into the strange behaviors of Betelgeuse was only just beginning. We had peeled back the veil of stardust, only to find a deeper mystery pulsing beneath. To look at a star is usually to witness a static point of brilliance, an unwavering sentinel that burns with a constant, steady light. Our own sun, from the perspective of a human lifetime, appears immutable. It rises, it crosses the sky, and it sets. Its output of energy so reliable that we have built our entire civilization upon the certainty of its warmth. But Betelgeuse is not like the sun. If we could strip away the distance and float alongside it, shielded from its fury, we would not see a static ball of fire. We would see a living, heaving entity. We would see a monster that breathes. The investigation into the dust cloud that blinded us in 2020 solved the immediate mystery of the great dimming, but it opened a door into a much deeper, more persistent question. What drives the violence of this star? The ejection of that colossal plume of plasma was not a random accident. It was the result of a mechanism deep within the star's interior, a rhythmic engine that has been running for millennia. To understand the future of Betelgeuse and to know when it might finally succumb to its explosive fate, we must place a stethoscope against its chest and listen to its heartbeat. We have known for nearly 2 centuries that Betelgeuse is variable. The English astronomer Sir John Herschel first quantified this in the 1830s, noting that the star seemed to wander in brightness, sometimes outshining the blue-white diamond of Rigel, and other times retreating into relative modesty. But it was only with the advent of modern astrophysics that we began to understand the cadence of this variability. It is not random noise. It is a complex, layered symphony of pulsations that tells us about the physical reality of the star beneath its glowing skin. The primary rhythm of Betelgeuse, its fundamental mode, is a cycle of roughly 400 days. For a little over a year, the star undergoes a transformation that defies earthly logic. It physically expands and contracts. This is not merely an illusion of light. The star itself grows larger and then shrinks back down. Imagine a balloon being slowly inflated and then deflated. Now, imagine that balloon is the size of the orbit of Jupiter. At the peak of its expansion, the outer layers of Betelgeuse push outward into the void, stretching the star's radius to inconceivable dimensions. As it expands, the gas cools and the star dims slightly. Then, gravity asserts its dominance. The outer layers fall back inward, crashing down toward the core. As they compress, they heat up, and the star brightens once more. This radial pulsation is driven by a mechanism that acts like a stellar valve. Deep inside the star's atmosphere, the intense heat strips electrons from atoms, creating an opaque barrier that traps radiation. The energy from the core, unable to escape, builds up pressure beneath this layer, pushing the star outward like the lid on a boiling pot. As the star expands, the gas thins out, the electrons recombine with their atoms, and the layer becomes transparent again. The trapped heat escapes in a rush of light. The pressure drops, and the star collapses under its own weight to begin the cycle anew. This 400-day heartbeat is the metronome of Betelgeuse. It is the steady, thrumming bass line of its existence. It is a violent process, moving vast oceans of plasma across hundreds of millions of kilometers, yet it is regular enough that astronomers can set their calendars by it. When we look at the light curve of the star over decades, we see this rise and fall, a sine wave of stellar respiration that has likely persisted for hundreds of thousands of years. However, the great dimming of late 2019 was not caused by this heartbeat alone. A simple contraction of the 400-day cycle is not enough to plunge the star into the depths of darkness we witnessed. The magnitude of the dimming required a perfect storm, a conspiracy of timing. This brings us to the second, more mysterious rhythm of the colossus. Overlaid on the reliable 400-day beat is a much longer, slower cycle. It is a long secondary period, or LSP, that takes roughly 2,170 days to complete, about 6 years. This cycle is far more subtle, a gradual swelling and fading of the light that operates on a timescale distinct from the fundamental breathing of the star. In late 2019, these two cycles, the fast and the slow, synced up in a catastrophic alignment. The 400-day cycle hit its minimum at the exact moment the 6-year cycle was also bottoming out. It was a moment of constructive interference, where the troughs of the waves aligned to create a super trough. The star was breathing out deeply, At the exact moment, it was also undergoing a long-term fade. This alignment created the conditions necessary for the disaster. The star was compressed, its surface gravity slightly higher, its atmosphere unstable. When the deep convection cell, the bubbling pot of heat we identified earlier, burst onto the surface, the shock wave from the star's internal pulsation gave it the kick it needed to escape. The heartbeat of the star essentially launched the bullet that became the dust cloud. But while this interaction explains the how of the dimming, the existence of the 6-year cycle presents a profound problem for astrophysicists. We understand the 400-day cycle. It makes physical sense for a star of this mass and density. The math works. We can model it in a computer simulation, and the virtual star behaves just like the real one. The 6-year cycle, however, is an anomaly. In the world of stellar physics, a pulsation period is directly related to density. A dense bell rings with a high pitch. A large, hollow bell rings with a deep, low toll. For a star to have a natural pulsation period of 6 years, it would need to be physically impossible, far larger and more diffuse than even Betelgeuse is. There is no known mechanism in the standard theory of stellar pulsation that allows a red supergiant to oscillate that slowly. It is like hearing a violin produce the sound of a foghorn. The instrument simply shouldn't be able to make that noise. This mystery forces us to look even deeper, past the convection zones, toward the hidden core of the star. Betelgeuse is a dying star, which means its engine is running out of fuel. For millions of years, it fused hydrogen into helium, just as our sun does. But that era is long gone. The core of Betelgeuse is now a layered onion of heavier elements. It has fused helium into carbon and oxygen, and it is likely now burning carbon into neon, magnesium, and sodium. These nuclear transitions are not smooth. They are erratic, susceptible to flashes and instabilities. Some astronomers have speculated that the strange 6-year rhythm might be an echo of this turmoil deep in the basement of the star. Could we be seeing the symptoms of gravity waves, not to be confused with gravitational waves, rippling through the star's deep fluid interior? Could the core be wobbling, sending slow-moving tsunamis of energy up through the mantle to disturb the surface years later? The problem with these internal theories is that the connection between the core and the surface of a red supergiant is tenuous. The star is so huge that the core is a tiny dense dot in the center of a vast empty cavern of gas. Information takes a long time to travel from the center to the edge. A pulse from the core would likely be dampened, scattered, or lost in the churning convection currents before it ever reached the photosphere where we could see it. So, we are left with a paradox. We have a heartbeat that we understand, the 400-day cycle, and a ghost rhythm that we do not. And yet, this ghost rhythm is powerful. It drives the behavior of the star just as much as the fundamental beat. In fact, some researchers argue that the 6-year cycle is actually the dominant factor in the star's mass loss, acting as a slow-motion pump that periodically primes the atmosphere for ejection events. The implications of this are unsettling. If we cannot explain the 6-year cycle with internal physics, then our understanding of red supergiants is fundamentally incomplete. We are missing a page in the manual of stellar evolution. And considering that Betelgeuse is the nearest laboratory we have for studying the death of massive stars, this gap in our knowledge is significant. This confusion has led to a scrupulous re-examination of the star's overtones. Just as a guitar string vibrates with a fundamental frequency and several higher-pitched overtones, stars pulsate in multiple modes simultaneously. Some recent studies suggested that perhaps the 400-day cycle isn't the fundamental beat at all. Maybe it is the first overtone, and the 6-year cycle is the true, fundamental heartbeat. If that were true, it would change everything. It would mean Betelgeuse is significantly larger and more luminous than we thought. It would mean the star is far closer to its final supernova than we dared to estimate. If the 6-year cycle is the fundamental heartbeat, then the bell of Betelgeuse is gargantuan, and the star is trembling on the very edge of stability. However, most astronomers have pushed back against this terrifying conclusion. The radius of Betelgeuse has been measured directly, and it doesn't quite fit the size required for the 6-year cycle to be fundamental. We are fairly certain the 400-day rhythm is the true heartbeat, which leaves the 6-year cycle stranded in the realm of the unexplained. As we watch the star today, recovering from its great faintness, we see the cycles continuing their relentless march. The light curve rises and falls, tracing the breathing of the giant. The 400-day beat continues to pump the bellows. The 6-year wave continues its slow, rolling modulation. They are currently out of sync, meaning the star is behaving relatively normally. But we know that in the future they will align again. The troughs will coincide once more. Another dark crisis will occur. And this leads us to an uncomfortable realization. If the physics of the single star cannot explain the 6-year rhythm, if the math of pulsations, convection, and nuclear burning fails to account for that slow, hypnotic cycle, then perhaps we are asking the wrong question. Perhaps we have been looking for the answer inside the star, when we should have been looking outside. Is it possible that the heartbeat of Betelgeuse is not entirely its own? Nature rarely tolerates a vacuum of explanation. When a phenomenon persists that defies the known laws of the object in question, it usually points to an external influence. We have modeled Betelgeuse as a lonely king, sitting in solitary splendor in the arm of Orion. We have assumed that the light we see comes from a single, isolated source, but the universe is rarely so lonely. Most massive stars are born in pairs, locked in a gravitational dance with a partner. We see them across the galaxy, binaries and trinaries swirling around one another. Could the ghost rhythm, the inexplicable 6-year cycle that nearly doomed the star's visibility in 2020, be the fingerprint of something else? Could there be a hidden hand tugging at the atmosphere of the red giant, a silent partner lurking in the glare? The heartbeat of the colossus is loud and clear, but there is a strange syncopation in the rhythm, a beat that skips and drags. As we move away from the internal mechanics of the star, we must turn our eyes to the darkness immediately surrounding it. The solution to the riddle of the 6-year cycle may not be a what, but a who. The star is breathing, but it is beginning to look like it is not breathing alone. When you stand in an open field and watch a hammer thrower in the moments before their release, you witness a distinctive physical dance. As the athlete spins, swinging the heavy metal ball around them on a wire, they do not remain perfectly planted in one spot. To counter the immense weight pulling away from them, they must lean back, shifting their weight, pivoting around a central point that lies somewhere between their chest and the heavy ball. If you were to paint the athlete in glowing neon and watch them from a kilometer away in the dark, you would not see the ball. You would only see the athlete wobbling, moving back and forth in a rhythmic circular pattern. Even without seeing the weight, the motion of the thrower would tell you, undeniable and clear, that they are holding something heavy. For decades, astronomers have been watching Betelgeuse with a similar suspicion. They have watched the red giant shimmy and sway, looking for the telltale wobble that would betray the presence of a hidden partner. And now, emerging from the mountain of data left behind by the Great Dimming and the subsequent scrutiny of the star, a consensus is forming. The heartbeat of the star, that strange, inexplicable 6-year rhythm we could not explain with internal physics, is likely not a heartbeat at all. It is an orbit. The ghost in the machine is real. Betelgeuse is not alone. The theory of the binary companion is one of those ideas in astronomy that feels almost too convenient until you look at the statistics. We often imagine stars as solitary wanderers, largely because our own sun is a single child. But in the wider galaxy, solitude is the exception, not the rule. This is particularly true for massive stars, the O-type and B-type giants that burn hot and blue before swelling into red supergiants. The vast majority of these stellar titans are born in litters. They form in dense clusters of gas and dust, where gravity pulls material into multiple cores simultaneously. It is estimated that over 80% of massive stars have a companion, and many have 2 or more. So, the idea that Betelgeuse might have a partner is not statistically unlikely. It is statistically probable. The reason we haven't found it sooner is simply a matter of contrast. Betelgeuse is so overwhelmingly bright, so physically expansive, that it acts like a lighthouse beam shining directly into our camera lens. Trying to spot a smaller, fainter star next to it is like trying to spot a firefly hovering next to a stadium floodlight. However, we do not need to see the firefly to know it is there. We just need to watch the floodlight move. Following the confusion of the Great Dimming, researchers at the Harvard-Smithsonian Center for Astrophysics and the Flatiron Institute began a meticulous excavation of historical data. They weren't looking for brightness changes this time. They were looking for movement. They analyzed the radial velocity of Betelgeuse, the speed at which the star moves toward or away from us along our line of sight. If Betelgeuse were a single, isolated object, its movement through the galaxy would be a straight line. It would drift through the local interstellar cloud at a constant speed. But that is not what the data showed. Instead, the star appears to be accelerating and decelerating in a rhythmic pattern. It is being tugged. For a few years, it moves slightly faster away from us, and then, for a few years, it slows down and moves slightly toward us. The timing of this tug-of-war matches the mysterious long secondary period perfectly. The wobble repeats every 2,170 days. This is the gravitational footprint of a companion star. By plugging the numbers into the laws of orbital mechanics, laws first penned by Kepler and Newton, astronomers have been able to sketch a profile of this hidden ghost. The invisible partner, now colloquially dubbed Betelbuddy by the internet, but more formally known as Alpha Ori b, is not a monster. It is likely a star very similar to our own sun. It probably has a mass roughly equal to, or perhaps slightly greater than, solar mass. In any other context, a star twice the mass of our sun would be a significant object. But next to Betelgeuse, which contains nearly 20 times the mass of the sun and is puffed out to a volume billions of times greater, the companion is a speck. It is a gnat buzzing around the head of a giant. Yet, gravity does not care about size. It cares about mass and distance. Even a small star, if placed in the right orbit, can yank a supergiant back and forth. The calculations suggest that this companion is orbiting at a distance roughly equivalent to the orbit of Saturn or Uranus in our own solar system. This places it uncomfortably close to the red giant. Betelgeuse is so large that if it were placed in the center of this system, its surface would extend out nearly to where Jupiter sits. The companion is skimming the outer edges of the giant's influence, threading a needle through the tenuous, dusty outskirts of the system. This proximity explains why the companion has such a profound effect on the light we see, and why it might have been the architect of the dimming events. It is not just a passive weight swinging the giant around. It is an active participant in the stellar weather. Think of the environment this small star must traverse. It is not moving through empty vacuum. It is orbiting inside the circumstellar envelope, the fog of gas and dust that Betelgeuse has exhaled over the last 100,000 years. As the companion star plows through this dusty medium, it acts like a boat moving through a calm lake. It creates a wake. Its gravity captures dust and gas, creating a localized shock wave, a bow shock that heats and disturbs the material around it. This interaction provides the missing link for the long secondary period of dimming. As the companion moves through its orbit, it likely drags a veil of dust with it, or perhaps creates a density wave in the surrounding cloud. When the companion passes between us and Betelgeuse, or when the wake it creates drifts into our line of sight, it obscures the light of the primary star. The 6-year cycle of fading is not the star itself getting dimmer. It is the dust plow of the companion blocking the view on a predictable schedule. This theory aligns beautifully with the chaos of 2019. We know the star's fundamental pulsation, the 400-day heartbeat, pushed gas outward. But perhaps it was the companion star passing through its periastron, the closest point in its orbit, or a specific phase of its cycle, that disturbed that gas, dragging it into a clump that eventually cooled into the great wall of dust. The companion didn't create the material, but it may have herded it into the position that blinded us. The existence of Alpha Ori B also forces us to reimagine the future of the system. We often speak of the Betelgeuse supernova as a solitary event, but if there is a companion, the dynamics change. When Betelgeuse finally explodes, this small, sun-like star will be in the direct firing line. It will be subjected to a bombardment of radiation and matter that is difficult to simulate. It will likely survive. Stars are resilient things, and the companion is dense and compact, but its atmosphere will be stripped, its surface scorched. It will be the sole witness, standing inside the blast radius of the greatest explosion in the local galaxy. For now, however, the companion remains a detected but unseen object. We have the gravitational math that says it must be there. We have the light curves that match its period, but we do not yet have a photograph. Capturing an image of Alpha Ori B is one of the most frustrating optical challenges in modern astronomy. The brightness contrast is extreme. Betelgeuse is roughly 100,000 times brighter than its suspected partner. In a standard photograph, the glare of the supergiant completely saturates the sensor, washing out everything in its vicinity. It is like trying to take a picture of a candle flame while staring directly into a high-beam headlight. However, the hunt is closing in. Astronomers are using a technique called interferometry, where multiple telescopes are linked together to create a level of sharpness that no single mirror can achieve. They are also using coronagraphs, instruments designed to block out the light of the central star to reveal the faint objects around it. The window of opportunity is opening. As the companion moves through its orbit, It is currently heading toward its point of maximum separation from Betelgeuse, a position known as a pastron. Calculations suggest that around the year 2027, the companion will be as far away from the glare of the giant as it ever gets. At that moment, the relentless gaze of the world's largest telescopes, including the European Extremely Large Telescope currently under construction, will be waiting. If the theory is correct, we will see a tiny, faint dot of light emerging from the red halo of the monster. If confirmed, the discovery of Alpha Ori B will be a triumph of deduction. It will validate the idea that even the most chaotic signals in the universe can be decoded if we stop looking at the object in isolation and start looking at the system as a whole. It reminds us that gravity is the invisible puppet master of the cosmos, connecting objects across the dark, forcing them to dance, even when we cannot see the strings. But the companion star does more than just explain the 6-year cycle. Its presence potentially solves another, even more perplexing impossibility that has plagued observers for years. It concerns the rotation of Betelgeuse. For a long time, data from the Atacama Large Millimeter Submillimeter Array, or ALMA, has suggested that Betelgeuse is spinning, and not just spinning, but spinning with a velocity that should tear it apart. The measurements indicate a surface rotation of 5 kilometers per second. For a star as large and puffed up as Betelgeuse, this is ludicrously fast. Conservation of angular momentum dictates that as a star expands, it must slow down, just as a figure skater slows down when they extend their arms. Betelgeuse should be turning leisurely, barely moving. Instead, the data says it is whirling like a dervish. The binary companion hypothesis offered a tantalizing solution to this impossible speed. The theory of stellar cannibalism was floated. Perhaps Betelgeuse wasn't always a binary. Perhaps it was once a triple system, and it swallowed one of its companions in the past. When a star consumes a planet or another star, it absorbs the momentum of that object, spinning up in the process. Was the rapid rotation a scar from a past meal? Was Alpha Ori B the survivor of a chaotic orbital merger that saw its sibling devoured? It was a dramatic, violent narrative that fit the monster persona of Betelgeuse perfectly. A cannibal star, spinning wildly from the momentum of its victim, with a second terrified companion looking on. But science is a self-correcting discipline. Just as the dust hypothesis replaced the cooling theory, and the binary hypothesis replaced the internal pulsation theory for the 6-year cycle, a new team of researchers began to look at that rotation data with fresh eyes. They looked at the colorful maps of the star's surface, the blue shift of the approaching side and the red shift of the receding side, and they asked a dangerous question. Is the star actually spinning? Or are we being fooled again? The discovery of the companion explained the wobble. It explained the long-term dimming. But the rotation speed was a different beast. And as we transition our focus from the gravitational dance of the binary to the surface of the giant itself, we find that what looks like speed might actually be something far more chaotic. The companion is real, but the spin might be a mirage, a grand illusion conjured by the boiling ocean of the star's atmosphere. We have found the ghost in the gravitational machine, and it has a name, Alpha Ori B. But to understand the spin, we must return to the surface, where the bubbles of plasma are rising with such ferocity that they can mimic the motion of a spinning world. We thought we saw a top spinning. We may have actually been looking at a pot boiling over. In the strict and often unforgiving court of astrophysics, Laws of conservation are the ultimate judges. Energy cannot be created or destroyed. It merely changes form. Momentum, once generated, must be accounted for. These are not guidelines. They are the rigid scaffolding upon which our understanding of the universe is draped. So, when an object as scrutinized as Betelgeuse appears to flagrantly violate one of these fundamental laws, it does not just raise an eyebrow, it sends a tremor through the entire scientific community. The violation in question concerns the rotation of the star. To the casual observer, the idea of a star spinning seems unremarkable. The Earth spins, the Sun spins, the galaxy spins. Rotation is the default state of celestial objects, a remnant of the angular momentum preserved from the swirling clouds of gas that birthed them. But for a red supergiant, spin is a complicated affair. Betelgeuse is in the final, swollen phase of its life. It has expanded from a relatively compact blue star into a tenuous red behemoth. The physics of this expansion dictate that the rotation speed must drop. Consider the classic analogy of the figure skater pirouetting on the ice. When she pulls her arms in tight, she spins a blur. But when she extends her arms outward, the laws of angular momentum force her rotation to slow down immediately and dramatically. Betelgeuse has effectively extended its arms to the very edges of the solar system. By all calculations, its surface rotation should have slowed to a crawl, perhaps rotating once every few decades, moving at a leisurely pace of mere meters per second. It should be virtually stationary in terms of rotational velocity. However, when astronomers turn the sensitive dish antennas of the Atacama Large Millimeter Submillimeter Array, ALMA, toward the star, the data told a different, impossible story. ALMA looks at the universe not in visible light, but in the radio wavelengths of the millimeter spectrum. This allows it to pierce through dust and see the cooler gas of the star's atmosphere. When the ALMA team analyzed the light coming from the eastern limb of Betelgeuse, they found the wavelengths were squashed, shifted toward the blue end of the spectrum. This blue shift meant that side of the star was rushing toward us. Conversely, the light from the western limb was stretched, shifted toward the red. This red shift meant that side was retreating away from us. This dipolar pattern, blue on one side, red on the other, is the classic signature of a rotating object. By measuring the degree of the shift, astronomers calculated the speed. The result was shocking. The surface of Betelgeuse appeared to be spinning at 5 kilometers per second. To put that into perspective, that is roughly 18,000 kilometers per hour. While that might seem slow compared to the speed of light, for a supergiant of this volume, it is blistering. It is hundreds of times faster than it should be. If the Sun were to expand to the size of Betelgeuse, its rotation would drop to nearly zero. For Betelgeuse to be spinning at 5 kilometers per second, it would imply that the star somehow gained a massive injection of angular momentum late in its life. For a time, this measurement fueled the wildest of the theories surrounding the star. This is where the cannibalism hypothesis gained its strongest foothold. If the star couldn't generate that speed on its own, perhaps it stole it. The idea was that Betelgeuse was once part of a binary system where the companion didn't just orbit, but was swallowed whole. As the smaller star spiraled into the envelope of the giant, its orbital energy would be transferred to the larger star's rotation, spinning it up like a whipped top. It was a violent, dramatic solution that explained the anomaly perfectly. But there is a razor in science known as Occam's razor. The simplest explanation is usually the correct one. and there is a team of researchers led by astrophysicists at the Max Planck Institute for Astrophysics who believed that the cannibalism theory, while cinematic, might be unnecessary. They proposed that we were not seeing a star that was spinning. We were seeing a star that was boiling. To understand this, we must return to the nature of the surface of a red supergiant. We cannot think of Betelgeuse as having a surface in the way Earth has a crust, or even the way the Sun has a photosphere. The Sun's surface is granulated, covered in millions of small convection cells, each about the size of Texas. They bubble up, release heat, and sink down, creating a texture like the skin of an orange. Betelgeuse is different. Because its gravity is so low and its atmosphere so deep, the convection cells are not small granules, they are titanic monsters. Simulations show that the surface of Betelgeuse is likely dominated by only a handful of these cells at any given time, perhaps 3 or 4 giant bubbles that cover the entire face of the star. Imagine a single bubble of hot plasma the size of the orbit of Mars. This bubble rises from the deep interior, carrying heat to the surface. As it rises, it is moving toward the observer. In terms of the Doppler effect, this rising motion creates a blue shift. It looks exactly like material moving toward us. Once the bubble reaches the surface and releases its energy, it cools and crashes back down. This sinking gas is moving away from the observer. The Doppler effect registers this as a redshift. Now, imagine looking at Betelgeuse through a telescope that, despite being state-of-the-art, still sees the star as a somewhat blurry disk. If, by pure chance, a giant rising bubble is dominating the left side of the star, and a giant sinking region is dominating the right side, what would the telescope see? It would see the left side coming toward us, blue shift. It would see the right side moving away from us, red shift. To the observer, this looks identical to rotation. The star appears to be turning, bringing the left side forward and sending the right side back. But it is a mirage. The star is not spinning on its axis, it is churning radially. It is the difference between a spinning globe and a pot of boiling soup, where the bubbles just happen to be rising on one side and sinking on the other. This is the convective nightmare of interpreting supergiant data. The movements of the atmosphere are so large and so violent that they mask the true rotation of the star. To test this theory, the research team turned to advanced 3D hydrodynamic simulations. They built a virtual Betelgeuse inside a supercomputer, a digital star that adhered to all the laws of fluid dynamics and thermodynamics. They let it run, watching the convection cells rise and fall, boil and churn. Then they did something ingenious. They processed the data from this virtual star as if it were being viewed through the ALMA telescope. They degraded the resolution, added noise, and applied the same blurring effects that real-world astronomers have to deal with. The results were damning for the rotation theory. In 90% of the simulations, the boiling motions of the non-rotating star created a velocity map that looked like rotation. The random distribution of rising and falling cells naturally created dipolar patterns that mimicked a spin of several kilometers per second. The impossible speed of 5 kilometers per second fell perfectly within the range of speeds generated by the violent upwelling of these convective bubbles. The implications of this study, published in 2024, are profound. It suggests that Betelgeuse is not a cannibal. It has not swallowed a companion star to spin itself up. It is simply a normal, albeit chaotic, red supergiant doing exactly what red supergiants are supposed to do: boil. The anomaly was never in the star. It was in our interpretation of the data. We were fooled by the scale of the convection. We imposed the logic of solid body rotation onto a fluid, turbulent atmosphere. This realization brings a certain calm to our understanding of the star. If Betelgeuse is not rotating rapidly, it behaves much more like a standard stellar evolution model predicts. We do not need to invent a catastrophic merger event to explain its current state. The Betelbuddy companion we discussed in the previous section is likely still there, safely orbiting at a distance rather than having been eaten. However, this illusion theory also complicates our ability to study the star. If convection masks rotation, how do we ever measure the true spin of a supergiant? Determining the rotation rate is crucial for predicting the supernova. A fast-spinning star explodes differently than a slow-spinning one. Rapid rotation can focus the explosion into narrow jets, potentially creating a gamma-ray burst, a focused beam of high-energy radiation that can be lethal to planets in its path. A slow rotator produces a more spherical, standard explosion. If the 5 kilometers per second figure is an illusion, and the star is actually rotating slowly, as theory predicts, then Earth is safe from any potential gamma-ray burst. We are not staring down the barrel of a cosmic shotgun. We are simply waiting for a conventional, albeit spectacular, fireworks display. The challenge now is to prove the illusion definitively. To do this, astronomers need higher resolution. They need to see the surface of Betelgeuse clearly enough to distinguish between the smooth, organized gradient of rotation and the patchy, chaotic blotches of convection. A true rotating star would show a perfect gradient, maximum blue shift at one edge, fading to 0 in the middle and increasing to maximum redshift at the other edge. A boiling star, on the other hand, would show a more clumpy map. A strong blue shift here, a patch of redshift there, perhaps a neutral zone in between. The ALMA data was just blurry enough to hide these clumps, smoothing them out into a gradient. Future observations with even more powerful interferometers, or perhaps observing at different wavelengths that penetrate to different depths of the atmosphere, will be the key. Astronomers are currently analyzing new data sets that track the rotation over time. If it is real rotation, the axis should remain constant. The star should keep spinning the same way. If it is convection, the pattern should change. The axis of rotation should appear to wander as old bubbles die and new ones rise in different locations. Preliminary hints suggest exactly this. The velocity map of Betelgeuse is not stable. The orientation of the blue and red patches seems to drift over timescales of a few years, far too quickly for a massive star to physically change its axis of rotation. This drift is the signature of weather, not spin. It is the shifting landscape of the boiling surface. So, the picture of Betelgeuse sharpens, ironically, by realizing that our previous picture was an optical illusion. We are looking at a star that is essentially a ball of hot gas held together by gravity, with a surface that is less of a solid boundary and more of a froth. The impossible speed was a ghost, just like the dimming was a shadow. This demystification does not make the star less impressive. If anything, it makes it more terrifyingly violent. To think that the bubbles on this star are moving at supersonic speeds, carrying enough mass to build thousands of Earths, and rising with such force that they can fool our telescopes from 650 light-years away. That is a testament to the sheer energy contained within a red supergiant. We are left with a star that is vibrating, pulsating, boiling, and being tugged by a hidden companion. It is a complex system, not a simple light bulb. And as we strip away the illusions, the dust that looked like cooling, the boiling that looked like spinning, we are left with the raw reality of the object. It is a star at the very end of its rope. The instability we see, the violent mass loss, the giant convective cells, these are the death throes of a titan. The illusions are fading. The reality is setting in. Betelgeuse is running out of time. And while we now know that it isn't spinning like a top and it isn't cooling into oblivion, we also know that the ultimate fate of the star is sealed. The core is burning its final reserves. The gravity that holds those giant bubbles in check is fighting a losing battle against the pressure of fusion. Soon, the illusions will stop mattering entirely. The dust, the spin, the companion, all of it will be swept away in a singular moment of blinding truth. The star is going to die. And thanks to our efforts to understand these anomalies, we now have a much clearer picture of what that death will look like. We are no longer afraid of a gamma-ray burst. We are no longer confused by the dimming. We are simply waiting for the inevitable collapse. The stage is set. The actors, the ghost companion, the dust clouds, the boiling surface have all played their parts in confounding us. But the final act belongs to the core. And when the core decides the show is over, the galaxy will know. There is a strange paradox at the heart of astronomy. The most violent events in the universe are often the most beautiful, and the most destructive moments are also the most creative. We have spent this documentary exploring the erratic life of Betelgeuse, peeling back the layers of dust, analyzing the phantom rhythms of its heartbeat, and debunking the illusions of its spin. We have come to understand it as a complex, dynamic system, a star that breathes, boils, and fights against its own gravity. But all stories, even stellar ones, must have an ending. And for a red supergiant, the ending is written in the laws of nuclear physics with unshakable certainty. Betelgeuse is burning the candle at both ends. Deep within its core, in a region no larger than a medium-sized city, the temperatures have reached billions of degrees. The star has spent millions of years fusing hydrogen into helium, then helium into carbon. It is currently moving through the heavier elements, burning neon, oxygen, and silicon. Each of these stages is shorter than the last, a frantic race to generate enough outward pressure to hold back the crushing weight of the star's outer layers. The final stage, the fusion of silicon into iron, is the endgame. It will last only a few days. Once the core is transformed into iron, the game is over. Iron is the nuclear ash of the universe. It cannot be fused to create energy. It absorbs energy. In that moment, the outward pressure that has supported the star for 10 million years will vanish. Gravity, waiting patiently since the star's birth, will win. The collapse will happen faster than a human thought. In a fraction of a second, the iron core, roughly the size of Earth, will implode. It will collapse in on itself at 25% the speed of light, crushing down until it is a ball of neutrons just 20 kilometers across. This abrupt stop, the slamming of matter against the unbreakable wall of neutron degeneracy pressure, will create a rebound. A shock wave of unimaginable power will turn outward, tearing back through the infalling layers of the star. This is the supernova. For the observer on Earth, 650 light-years away, the news of this death will not arrive instantly. The first messenger will not be light, but neutrinos. These ghostly particles, generated in the trillions during the core collapse, interact so weakly with matter that they will fly straight through the star's dense envelope as if it were not there. They will race across the galaxy at nearly the speed of light, arriving at Earth a few hours before the visible flash. Buried deep under mountains in Japan, Antarctica, and Italy, giant tanks of pure water and liquid scintillator, detectors like Super Kamiokande and Ice Cube, will suddenly light up. Their sensors will register a spike of neutrino activity, the silent alarm of the cosmos. Computers will cross-correlate the signal, and a notification will go out to astronomers around the globe. Something huge has just died. In those few hours of waiting, the telescopes of the world will slew toward Orion. The amateur astronomers, alerted by the buzz of the scientific networks, will set up their tripods in backyards. And then, the shockwave will reach the surface of Betelgeuse. This moment, known as shock breakout, is when the fireworks truly begin. As the energy from the core finally punches through the dusty, boiling photosphere, the temperature of the star's surface will spike to hundreds of thousands of degrees. A blinding flash of ultraviolet and X-ray radiation will herald the arrival of the explosion. To the naked eye, the red star will suddenly change. It will brighten rapidly, turning from its familiar ruddy orange to a piercing electric blue-white. Within days, it will climb the magnitude scale, surpassing Rigel, surpassing Sirius, surpassing Venus. Models predict that at its peak, the Betelgeuse supernova could shine as brightly as the half-moon. Imagine the sight. You could step outside at midnight and read a book by the light of a dead star. The familiar constellation of Orion will be transformed, its shoulder blazing with a cold, intense fire that casts distinct shadows on the ground. The light will be so intense that it will pierce through thin cloud cover. Even during the day, the supernova will be visible. It will be a pinprick of brilliance against the blue sky, a second daytime star that you can spot on your way to work or school. It will be a global phenomenon, a shared experience for every human being on the planet. For the first time since the invention of the telescope in the 17th century, humanity will witness a galactic supernova in our own neighborhood. It will inspire art, music, and literature. It will be a cultural touchstone, a reminder of our place in a dynamic universe. But amidst the awe, there is often fear. When we speak of explosions and radiation, our instinct is to look for a bunker. The internet is already rife with sensationalist claims that the Betelgeuse supernova will strip our ozone layer, irradiate the surface, or cause a mass extinction. We can put those fears to rest. The universe is indeed a dangerous place, but distance is the ultimate shield. A supernova kill zone, the radius within which the radiation is intense enough to destroy an atmosphere, is estimated to be about 50 light years. Betelgeuse is more than 10 times that distance away. The wave of X-rays and ultraviolet light that hits Earth will be absorbed by our upper atmosphere. It might cause a slight ionization, perhaps disrupting some high-frequency radio communications for a short time, and the ozone layer might take a minor hit comparable to a solar flare, but the biosphere will be safe. We are in the splash zone where we get to see the show, not in the impact zone where we get burned. The neutrinos will pass through our bodies harmlessly, as billions of solar neutrinos do every second of every day. The shockwave of gas, the physical debris of the star, will take 6 million years to reach us, and by then it will be so diffuse it will be nothing more than a gentle breeze in the solar wind. So we can watch without fear. We can marvel at the violence without being its victim. The light show will last for months. The supernova will stay near peak brightness for a few weeks, fueled by the radioactive decay of nickel and cobalt forged in the explosion. Then, slowly, it will begin to fade. As the months turn into a year, the piercing blue light will redden and dim. It will drop below the brightness of the full moon, then below Venus, then below Sirius. Eventually, it will fade from daytime visibility, returning to being a creature of the night. And then, one day, perhaps 2 or 3 years after the explosion, a keen-eyed observer will look up at Orion and notice something missing. The shoulder will be gone. The bright red star that anchored the constellation for millennia will have faded below the threshold of human vision. The hunter will be missing an arm. The geometry of the winter sky, which we assumed was eternal, will be permanently altered. But the story of Betelgeuse does not end with the fading of the light. In the place where the star once stood, a new object will act as a monument to the fallen giant. The debris from the explosion, layers of hydrogen, helium, oxygen, carbon, and iron, will continue to expand outward at thousands of kilometers per second. Over centuries, this debris will form a spectacular nebula. It will be a twisted, glowing tapestry of gas, illuminated by the energy of the remnant left behind. We see these remnants elsewhere in the sky. The Crab Nebula, the wreckage of a supernova observed by Chinese astronomers in the year 1054, is a tangled web of filaments that is still expanding today. The Betelgeuse Nebula will be closer and larger, likely becoming one of the most studied and beautiful objects in the telescope eyepieces of future generations. At the center of this nebula will sit the corpse of the star. Given the estimated mass of Betelgeuse, between 15 and 20 times that of the Sun, the core will likely not be heavy enough to collapse into a black hole. Instead, it will stabilize as a neutron star. This object will be a city-sized sphere of matter so dense that a single teaspoon of it would weigh 1 billion tons. It will likely be spinning rapidly, conserving the angular momentum of the core collapse, and it may possess a magnetic field trillions of times stronger than Earth's. If the magnetic poles are aligned correctly, it will sweep a beam of radio waves across the galaxy like a lighthouse. Betelgeuse will have been reborn as a pulsar. There is a profound beauty in this transformation. The death of the star is the birth of the elements. The calcium in our bones, the iron in our blood, the oxygen filling our lungs, all of these heavy atoms were created in the cores of stars that died long before the Earth was born. We are, in the most literal scientific sense, made of stardust. When Betelgeuse explodes, it will seed the local interstellar cloud with a fresh batch of these building blocks. It will cast out carbon, silicon, and gold into the void. This material will mix with the surrounding gas, cooling and condensing over millions of years. Eventually, gravity will pull these enriched clouds together again. New stars will ignite. New planets will form from the dusty disks around them. And perhaps, on one of those future worlds, built from the ashes of Betelgeuse, a new form of life will look up at the sky and wonder where it came from. This is the great cycle of the cosmos. It is a recycling system on a majestic scale, where death is the necessary precursor to new life. Betelgeuse is not just a light in the sky, it is a participant in this galactic ecology. Its erratic behavior today, the dimming, the pulsations, the mass loss, is the labor pain of this creation process. We do not know exactly when the fire will start. The soon of astronomy is a frustratingly vague concept. It could happen tomorrow. It could happen next Tuesday. Or, more likely, it could happen in 10,000 or 50,000 years. In the grand sweep of cosmic time, 50,000 years is the blink of an eye. But for a human civilization that struggles to plan beyond the next fiscal quarter, it is an eternity. There is a distinct possibility that none of us alive today will see the great flash. We may live our entire lives with the red supergiant blinking erratically at us, keeping its secrets, teasing us with its wobbles and its dust clouds. We may pass the torch of observation to our children and their children, leaving the vigil of Orion to future generations. But even if we do not see the finale, the study of Betelgeuse has already given us a gift. It has forced us to refine our understanding of the universe. The mysteries of the great dimming challenged our models and made them better. The illusion of the spinning surface taught us humility and the importance of questioning our data. The search for the companion star reminded us to look for the hidden connections between things. Betelgeuse serves as a reminder that the night sky is not a painted backdrop. It is a deep, three-dimensional wilderness filled with objects that are evolving, changing, and interacting. It invites us to keep looking up, to keep asking questions, and to find comfort in the fact that while we are small and our lives are short, we are part of a universe that is vast, ancient, and endlessly creative. So, the next time you find yourself under a clear winter sky, find the hunter. Trace the line of the belt, look up to the bright, ruddy shoulder, and take a moment to really see it. Don't just see a dot of light. See the boiling ocean of plasma. See the dust clouds drifting in the stellar wind. See the hidden companion tracing its silent orbit. And see the time bomb ticking down to the moment of glorious transformation. It is Betelgeuse. It is our neighbor, our mystery, and our future history. And it is arguably the greatest show in the galaxy, just waiting for the curtain to rise.